want to start recording. That's the first thing I want to do, and say hello.
Hi.
Hello. So I apologize for all the email drama over the weekends, but I'm pretty sure the homework system is working. Can anyone tell me otherwise right now? It's working. Okay, yeah, I had a heart attack on Saturday because I was doing the math in my head. I have 63 students across my 2 classes using this system, and that would be 11 homeworks across times 63 people, and I was like, oh my God, like, so no. The problem was that the company we used changed over to a different server, and they told us we had to update our configurations, and I thought we had, and it turned out we had missed a part, and so, but it was solvable, and they gave me a backup data set for homework 1, so I believe there is no data lost. I believe that is true, but please print a copy of it to PDF when you finish it, just in case something goes wrong, because then I can easily see like that you did it and that you had all the green numbers right, and I can grade the rest of it by hand if it comes down to that. But I believe everything is working. Since the system was offline for a couple days, I extended the deadline for homework 1 to Wednesday night. So you have some extra time to that. And 1 more office hours tomorrow in case anyone wants to get any help from me. When are your office hours, Erica? Tomorrow as well? Okay, yeah, so if I need to extend deadlines, they'll usually go to Wednesday for that reason, so that we have 1 more day in class and then the next day. If we get behind, I'll extend deadlines. The next thing you have to do after homework 1 will be a formative assessment. That is not up yet because I wanted to see how far we got today before I figured out what questions to ask. And after that will be homework 2, and I'll let you know when that's available. So, all right, anything I'm forgetting in terms of logistics and stuff like that? Hello, Zoomers. I'm going to start the screen share. How about that? Anything? We're good? All right. Yeah, let's do that. So I'm hoping that we can start example 2 today. But my experience in dealing with the tech issues of the homework system reminded me of what it feels like to be in the weeds with words you don't know and letters you don't know, and someone says, it's just this, fix it, and I don't know what this sentence means. So I thought maybe a little bit of like review and recap would be a useful thing. Maybe a little bit. Okay, in particular, the idea of how the pieces fit together in significance testing. I made us a little spreadsheet that we can go over, and I'm going to post it when I'm done with it after class, so you don't need to write anything, okay? This will just be a little play-along deal. So I have this picture as our labeling system for how we're going to talk about slopes. Slopes meaning relationships between variables, and that so far we have either a quantitative predictor having a slope and predicting a quantitative outcome. At the end of last week, we introduced a binary predictor predicting a quantitative outcome. So 1 slope for 1 predictor thus far. So let me zoom in just a little bit here so maybe we can see it. So let's say that my slope is 6. Could I have a slope of 6 in my output? Sure I could. What does that tell me? Could someone please put 6 into a sentence? And Zoomers, you can play along too. You can talk or type. Yep, that's where I'm going. Give me a sentence, please. Yes. Yes, so for every 1 unit increase, like up, as x goes up by 1, y goes up by 6. Okay, what about negative 6? Someone want to try a sentence with that one?
Every 1 decrease.
I go the other way. I'd keep x going up and change y. So for every 1 unit higher x is, what happens to y?
It increases to 6.
If it's negative,
Okay.
1 word different. And you can phone a friend if you want to. Make someone else answer. You want to try?
For every 1 unit of increase of x, the y decreases by 6.
Yeah, so then they go in opposite directions. Yep. Yes, so you can talk about it the other way. So it's less intuitive, but it's equally correct to say if I have a positive slope of 6, that as x goes down by 1, y goes down by 6. That's equally correct, but people don't talk about it that way. The key idea is, do they both go up, or does one go up and one goes down? Both goes up is a positive slope. One goes up and one goes down is a negative slope. Which is bigger in terms of describing the size of the relationship? They're the same. Yeah, it's equally strong in terms of how related X and Y are. They're just related in different directions. Okay, so next column over. So slope estimate is whatever number makes the sum of the squared residuals, the e's, collectively the smallest. And there's math that you can figure that out. It's actually a matrix equation, X transpose X inverse X transpose Y, I believe. You don't need to know that. I only know that because I've had to memorize it before. But point being, math is why. And your textbook has some nice visuals of the idea of minimizing residuals, but that's where it comes from. Next column over, and I organized this, by the way, because this is what it's going to look like in your output in the examples that we'll show you. Slope standard error. What if it were 2? What would that number tell me? Staring at the camera too, Zoomers, I'm here for you. Go for it.
Take a guess.
Okay, this is a harder one.
It's the average, you would be off from 6 if you had another sample?
Yes, so 2 is how far off from the population slope you would expect your sample slope to be on average. So like you're wrong by 2 on average is what that's saying in terms of what the right answer is in the population. Now, do we ever know what that is? No, pretty much never, unless you actually have the entire population and that's all you care about. But if you make up the data, you do. I can say that much. So 2 conveys the expected inconsistency of the slope across samples. So sometimes it could be 4, sometimes it could be 6, sometimes it could be 8. It's wiggly. Now, if I take 6 and divide by 2, that gives me 3. That ratio, the estimate minus the null hypothesis, so I have the formulas in here, null hypothesis of 0 in the first column, because that's usually what we work with. Slope estimate divided by null hypothesis. What's a null hypothesis again? More vocabulary.
There is no relationship between variables.
Yes, the null hypothesis, if you said HO is 0, means we're expecting the slope to be 0, meaning the line is flat, meaning as x goes up, we don't know what's going to happen to y. Nothing. So estimate minus HO. How different than expected is your slope? That's the numerator. Divided by how wiggly it is on average. That's your standard error. And I'm going to say wiggly, because if you think of it as repeated samples, it's not always going to be 6. The standard error says it's going to be off by 2 on average from what it's supposed to be. So T is our new friend here. That ratio of estimate minus null hypothesis divided by standard error, T is a test statistic. And that hopefully will be the last time you hear me say that. T value the rest of the semester. So think of it this way. The numerator is what happens. The denominator is what's usually expected to happen. So how weird is it is a ratio of what happened to what should have happened. If I think about these numbers in terms of units that go into them, a slope estimate is the change in y for a 1 unit change in x. So I have something like this in terms of the units. Standard error, the numerator of that is formed by the residual variance of y. The denominator is a function of the variance of the slope, or excuse me, the variance of the predictor it is the slope for, so x variance, as well as sample size and degrees of freedom. So it's still kind of y divided by x. Well, if we take the estimate and divide by the standard error, the units cancel. So t is unit free at this point. T is a standardized way of expressing how far from expected your slope estimate is, taking into account its expected variability or wiggliness. So if I have a t of 3, that alone doesn't tell me what's going to happen. I have to compare that to a t distribution. And how tall it is depends on how many people you have. and how many parameters you've already spent. So what happens with the t-distribution is the more people you have, the tighter it gets. The fewer people you have, the flatter it gets, and the more area is in the unexpected section. So let's say that my denominator degrees of freedom are 8. Two-part question. How many people must I have had to start with? Got one vote for 10. Anyone else want to take a vote? How do I know that? K is what again?
Number of estimates.
Number of fixed effects in this case, yep. So I had to have a fixed intercept and a fixed slope. Fixed intercept is always there. The question is, what else do you need? So that's the 2. So to end up with 8, I had to have had 10 people to start with. Now, is 10 a good sample size? Would you have a lot of faith in like a survey of 10 people? No, I wouldn't, at least. But maybe it's a pilot study. Maybe these are subjects that are very difficult and time-consuming to get to. So I used to work at the Lifespan Institute in KU, and they studied a lot of special populations, like children who had Prader-Willi syndrome or other kinds of genetic conditions where it's very rare. So like they had a sample of 50 kids, and it was the largest in the nation, because these are very difficult to track down children. So T critical is where the goalposts are. These goalposts, this is programmed, by the way, this is a function inside Excel that will do this for you. At an alpha level of 0.05, meaning 5% is where unexpected is, 95% is where expected is, using this denominator degrees of freedom, the goalpost is 2.3. That's at alpha of 0.05. If our t is 3, what do we conclude? Is 3 bigger than 2.3? We're outside the goalposts. So then how would I talk about that? Using the language in this picture, and you have 4 choices: significantly negative, non-significantly negative, significantly positive, and significantly positive. Yeah, so we know it has to be positive, right? Because 6 is positive. T is signed, by the way. So you'll note the 2 conditions here with the negative slope have negative t's, not a coincidence. So we know that if we're talking about the positive slopes, that we are in positive land. If we're past the goalpost of 2-ish, then I would call this significantly positive, meaning our p-value, which is the exact p-value is right here, is 0.0171. That means if the true slope in the population were 0, we would see a slope of 6 less than 2% of the time. It's in unexpected territory, I'm making up words. You'll note that I'm back to Fresca today because I've already had all the caffeine, and at some point, too much caffeine makes me come back down. You know what I mean, right? Mm-hmm. Yeah, there's a caffeine curve. There's not a linear relationship. So what if reviewer 3 comes back and says, you're doing too many tests. If each one is 5%, you have alpha inflation. I don't like it. Well, okay, I'll be more conservative. So let's do alpha 0.01. That's redefining where unexpected starts. It's literally moving the goalposts. So now the goalposts start at 0.5% over here and 0.5% over here, as opposed to 2.5 over here and 2.5 over here. So now the goalposts are at 3.3. What do we say? Yeah, if this is our standard, 3 is less than the goalpost. We're inside. So we're in this section right here. 6 is positive, but it doesn't meet the goalpost, doesn't meet the standard. These 2 columns are largely unnecessary anymore because what you will get instead is this column in your output, the exact p-value. A p-value is the probability of finding what you found if the null hypothesis were true. So this result would be expected to happen 1.71% of the time. which is less than 5% of the time, but not less than 1% of the time. Alpha is something you're supposed to decide about ahead of time for obvious reasons, right? It's like, well, I'm going to be conservative. I'm going to pick an alpha of 0.01. And then you're like, oh, actually, I meant 0.02. Can I change my answer? Yeah, that's called p hacking. When you're trying to find significance to get published, that's usually not good. So let me fill in the blocks here. So if alpha were 0.05, we said this would be significantly positive. If we switched it to a more conservative alpha, we would say non-significantly positive. There we go. Okay, how are we doing so far? Thumb check? Sideways to up? I'll take that as a win. Zoomers? All right. Next line. How does the story change? What's different? Zooming in. Yeah, that number right here. Now what I'm saying is, what if we expect the slope to be more wiggly on average, more inconsistent across samples? What does that do? It brings down my ratio. The numerator is still what happened. The denominator is what did you expect to happen? Now we expect more variability. So what happened is not as impressive. So we have the same critical values, but now t is 2 instead of 3. That generates a p-value of 0.08. So what do we call that regardless of which alpha we stick with? Yeah, non-significantly positive on that one. Nin. I know. You cannot type while people are watching. That is a rule. You also cannot do math while people are watching if you're me. Watch that. Copy paste for the win. Yes. And again, I will post this after class. You don't need to worry about this. What about if it's -6? How does my story change? Yeah, so then we're talking about being on this side of the fence. That's weird. Non-significantly negative if we're using an alpha of 0.01, significantly negative if we're using an alpha of 0.05, and then non-significant either way if we're using an alpha of, if we have a larger standard error. So T is a standardized way of talking about how far from expected you are. How many standard errors away? Doesn't matter what the units are at this point, it's standardized. Okay, any of that you want to hear again or differently? Good. Okay, now watch what happens if I decide to get a bigger sample. Let's say that my 8 people were my pilot study and NIH liked what I did, and they're like, here, have $1 million, go find some more people.
Yay.
That'd be nice, right? Or IES or NSF or Spencer or any other place that's going to give you money to do research. Let's say they gave you enough money for 500 people and you could find them all.
So that's 498, that's not 500.
It is, though. 498 is degrees of freedom. Yeah, because we're still only spending 2 parameters. So we got a lot more left over. The story has not changed otherwise. What has changed? The goalposts. They're further in. It's easier to kick the ball away. Exceed the goalposts if you have more sample size. So if you look at the corresponding p-values, they're all smaller. So we could argue this is the same set of results in terms of how strong the relationships are. What has changed is how certain we are about them. They are less likely to happen if the null hypothesis is true. We have more certainty in that because we have a larger sample size. So just having significance is not the end of the story. If I have 10,000 people, everything is significant. So that distinction stops mattering at some point. And that's why you have an article, the Earth is round, p less than 0.05, arguing that point. So what else should we talk about then to try to give more context to our results being significant or non-significant beyond just the direction? This is a topic introduced at the end last time. 6. Do I know if 6 is a lot? I just gave you X and Y, right? I didn't tell you if that's dollars or inches or, rating scale points or whatever. 6 could be a lot or it could be not a lot. That doesn't matter with respect to significance. So what am I talking about? Trying to figure out how much is this in like an absolute kind of standardized way. 2-word phrase. First word starts with an E. Second word starts with an S. Yay, effect size. Yes. That's one more piece of information that we're going to want to have. Effect size is a way of talking about, in unitless measures, how strong an effect is. There are 2 main families that you'll see this semester. One is R, correlation effect size. The other is D, standardized mean difference. Let me go back to where we started talking about those things. Remember R? Like there's multiple kinds of correlations. The one that we'll deal with in this class is a Pearson correlation. So R is an effect size that ranges from -1 to 1. So if I tell you that I have an R of 0, what does that mean? Yeah, no correlation, slope is 0. We just need to rescale our slope of 6 into a standardized metric. And we can do that a couple different ways. If I only have one predictor, the easiest way to do it is to think about z-scoring my 2 variables. If I translate x into a z-score scale, that means give it a mean of 0 and a standard deviation of 1. If I do the same thing for y, then my 6 becomes a correlation. The other way to do it is if you have more complex models, then there are handy-dandy formulas built around t. So if you have t and you have denominator degrees of freedom, you can use that to get an R, a correlation effect size, or you can use it to get a D, which is a standardized mean difference. A D of 0 means no difference, but D is unbounded. It goes from -infinity to +infinity. It's the number of standard deviations different 2 groups are in terms of their means. So this was the slide that I tripped over last time, and I'm going to do a better job this time. That's my plan. Think I can do it? I better. It's my job. Like, you have one job. Like, actually, I have a lot of jobs, but in this moment in time, I need to not screw up this slide. That's my goal. So if I think of effect size as a continuum, we talked about dividing lines, right? Goalposts. Ding, ding. And on one side of the goalpost, towards the 0 side of effects, meaning no differences, no slopes, no relationships, we would call something not significant, is p is greater than or equal to alpha. So if p is exactly 0.05 and your alpha is 0.05, that's non-significant. It's supposed to be less than. On the other side of the goalpost, if p is less than alpha you chose, we would say it is significant. What depends where, nope, sorry, screwing it up. Where this blue line is located is a function of sample size. More people, which way does it go? It's like, yeah, wait, this doesn't work here. More people means it is easier to call something significant. It moves to the left. If you have fewer people, it moves to the right. You have to have a stronger signal to say it is meaningfully different than 0. It is significant, unexpected. So you can anticipate what kind of sample size you would need to be able to detect an effect reliably, and that brings us to something called power. And several folks nodded at the end of class last time, having heard this. Do we want to talk about this? I'm going to give you 2 choices. We can either finish talking about concepts or we can go to an example that actually does stuff. What do you feel like? Do stuff? Stuff. We're voting stuff? All right. Okay, bye-bye slide that I keep messing up. How about, let me save this, get that out of the way. How about example 2 then? We know enough to get through a lot of this. This is posted on the website as a PDF file. This is the Word version of it. All of the original source files are in the zip folder that go with it. That way you can use those to work on homework too. So this is the same data set that we played with in example 1. It will stay with us through example 4. The 2012 General Social Survey, so this is a US study. And I picked this data set because I know there's folks from every different discipline across the university in this class, and I didn't want to pick something that would be too specific to one area. So I picked this because it has things like money, education years, grouping variables, like things that would be relatively straightforward to understand regardless of what field of research you're from. So first steps first, I'm going to show you and walk through the code that you would need to import your data in Stata and then in R. If you want to run things along with me in your package of choice, go right ahead, but I have everything in this handout that you should need. That way you don't have to worry about keeping up. You can just listen and follow along. So Stata, CD means, hey, where's my stuff at? Where's the working directory? And if you use the virtual desktop and you use a file that's stored on your local machine, you need this prefix right here, //client/C. This is why if you're using the virtual desktop, I recommend that you use Windows Explorer to navigate to where your stuff is so you can see what it calls it, and you'll see that it adds this prefix. If you're using the H drive that's already mapped to the university, you don't need this. I have 2 commands here. Clear is first, meaning if I had a data set open, get rid of it because I want to do something else. And then I'm importing data in Excel. I tell it what the name is in quotes. Anything that is red and in quotes like this is both case and space sensitive. You have to type it exactly or it won't understand. Because Excel can have multiple worksheets, I tell it which worksheet to pull from. Case preserve means don't change things to lowercase letters. Let them be a mix of whatever I typed. First row means grab the variable names from the first row of the spreadsheet. And then clear means if it's already in here, like re-import it. So let's say that you import your data, you do something and somehow you screw up your data set. That will happen to you. I can guarantee it. It happens to me like at least once a day. That's not a tragedy because all you need to do is just rerun this and your data set comes right back in the way it was. So as long as you have the original that's intact, whatever you bring into a program, you can work with as much as you need, but you can always get the original back. I added labels to the variables that we're going to be paying attention to. I have Mary is whether or not someone is married, and it's dichotomized into 1 means unmarried and 2 means married. Education is in years, that's the variable that we've been looking at, and income is in thousands of dollars. So what I'm showing you in this example is where all the numbers came from that were in my PowerPoint. Like this is the behind the scenes part. So you saw the end result, now you see the process that led to that result. Okay, folks trying to learn Stata, any questions about any of this thus far? So the name of the column is right here. That's what you're going to be typing. This is an extended label that makes it more easy to read your output. In R, I have noted that I'm using these packages in this example. You have to have installed them and loaded them ahead of time. And in my examples, that's the first thing you'll see is code that says if this package doesn't exist, install it and then load it. If you've already installed it, all you have to do is load it, but this can take a few minutes. So if it's churning, just be patient. You'll see a bunch of text scroll across your console that knows it's doing something. Just like in Stata, the first thing I want to tell it is where my stuff is. So here's my working directory for this set of example files. I am going to read in an Excel file using read Excel as a function that is within this read Excel package. Tell it what sheet it is. Things in quotes, again, case and space sensitive. And then sometimes, depending on what type of data set you brought it in, whether it's native to SAS or SPSS or R or other things, it imports as something other than a data frame. There's other kinds of data. So honestly, for superstitious reasons, I always have this because I don't want to guess. Make it a data frame because that's what you need it to be in order to do analyses. And R doesn't like labels in the data sets for certain routines, so I've gotten in the habit of not having them. So if you look in the original documentation, I have labels as comments only, just for the user's knowledge. They won't show up on the output. Okay, so first things first, description. No matter what you're doing, the first thing that you would want to do is print descriptive statistics to make sure that your data are correct. For instance, if you have a variable that you know should be 1, 2, 3, or 5, and you get a 7 as your maximum value, stop. Do not pass go, do not do anything else. Likewise, watch for things like minus 99 as a value that it's reading. That means it's a missing data code it did not understand properly. So I'm looking at summarizing. That's the command if you have a quantitative variable or a binary variable will work. And I'm asking for it to summarize 3 different variables right here. So you can stack them up and have multiple in the same command. Comma means options. So after a comma are options for what you're asking for, and detail means give me everything. So I have a couple of values highlighted here. The mean of income is 17.3. That's going to show up in our output in just a minute. Its variance is 190, and variance is unintuitive, right? What is variance again? Vocabulary words. I'll take gestures, definitions, words.
Average square distance.
Average squared distance? What does it look like in gestures? Yeah, this. How wide it is. So more variance, more wide. So if this is the average squared distance, how do we turn it into the average distance?
Square root.
Yeah, square root it. Cough, cough. Homework questions. Yeah. Homework 1 was vocabulary drill, right? Find the average distance from the mean. Like, oh, what is that? Standard deviation. Okay, where's that at? So 13. So 13.8 squared gives us our variance here. So this is how far off from the mean each person is relative to the sample mean of 17. So this is describing the people in one sample right now. If I asked you for the median, is that on this output? 50th percentile, that is your median. That's the middleist number. If you have a data set with an odd number of observations, then there will be a true middle. But if you don't, then it will have to be extrapolated between the 2 middleist values, and programs do that a little bit differently sometimes. Is income positively or negatively skewed? Yeah, how do I know that? Because this is a positive number. Yeah. So that means that which side of it has more people, the left or the right side? Yep, more gestures. Left side has more people. Yeah, it's named towards which way the tail goes. So positive skew means that you have a lot of people on the left side and then comes down like that. Negative skew would be the opposite. And if we look at these 2 numbers, that also indicates skewness. So if we have a mean that is larger than the median, that implies there's a tail that's bringing it up. It's stretching it towards the right side of the graph. Okay. Years of education. On average, 13.8. So when people center variables, what is centering again? Add or subtract, yep. Yet we're shifting the scale of x by some constant so that 0 is within the realm of that variable. A common thing that people do when they center is mean center, what they call it, or grand mean center, which means to subtract the sample mean. So that's fine. Like I could subtract 13.81199 and from my scores, and then the mean of education would then be 0. But then who is my reference person if I were to put education in the model as a predictor? Someone who had 13.8111. Do you think anyone wrote that down as their answer? Nope, that is like most of the way to an associate's degree, maybe 2-year degree, but not all the way. I guarantee no one wrote that down. So I don't prefer mean centering. I prefer picking a number that has meaning in terms of the context of the variable when possible, or picking a number near it. So I picked 12 when I built the example because then my reference person is a high school graduate. You don't have to just pick the mean. But it's helpful to know the scale of this to interpret the rest of it. Variance then, that's my average squared offness. If I take the square root of that, my standard deviation is almost 3. So on average, people differ from the mean by about 3. And this variable, median is 14, skewness is negative. So the tail is on the left side for this variable just a little bit. Marital status. Now this is a weird one. Is this quantitative or categorical?
Categorical.
Categorical, but we can treat it as quantitative because there's only one difference between a 1 and a 2. So we talk about a 1 unit change. That's moving from the 1 group to the 2 group. But I'm not going to leave this variable like this because if I left it like this, who is my intercept about? So if 0 is not within the scale, right, the intercept refers to somebody who doesn't exist. So I'm going to end up subtracting 1 to turn this into a binary variable where 0 is unmarried and 1 is married. They're split about half and half. So 46% of the sample is married. According to this, that's given by the mean of 1.5. So even though this is indeed a categorical predictor, we can treat it as quantitative. If I had 3 or more groups, we can't, and we got to do something different, but that's unit 3, down the road. All right, descriptions in R. I am using a package called Psych, so it was written by a psychologist, Bill Revell, and he has a function called describe that does a whole bunch of summary statistics at once, so that's handy dandy. The code to it is more complex. So do you remember at the beginning of the semester I said state is easier? Here's a good example. Summarize. What would you like summarized? These things. The end. To do that in R, I have nested sets of parentheses. So if I go on the inside right here, this much. Actually, yeah. Yep, that's right. I think I'm missing one right here, actually. I need to double check that. This does not look right. That looks right to me. I will double check it though. X means what's your name of your data set? So this name is whatever you called it. Mine's called example 2. I would like to summarize all the rows. That's why there's a blank space here and then a comma after. You just have to know that. What would you like to summarize? These 3 things. So I am building a list. C means concatenate, like stack them together into one thing. Fast equals true means don't spit out everything. There's extra stuff that you could ask for that's not in here. And then finally, the print command here is to make sure that I have enough digits to give accurate answers to the homework system. So I picked 3 in this case. So here's the same information. Our mean of 17.3 for income that we're going to see in just a minute. And much to my dismay, what is missing from my list? Yeah, it doesn't give me variance. And there's no way to ask for it. Bill, what are you thinking? Can you please add variance to describe if you're listening? You never know. I'm actually going to see him at a conference next month. I'll ask him to put variance in there. I know. Like, what are you doing? Bill Revell. He is at Northwestern, I believe, in the psych department. So there's a way around that. Base R has a function called var. That stands for variance. So I'm asking just for that much information. When I ask for it for multiple variables at a time, though, I get this thing. We're not going to see this much this semester, but if you take further classes, you will. This little thing is a matrix. 3 rows, 3 columns. It is a square matrix, meaning that the same information is in multiple places. So row 1, column 2 is the same as row 2, column 1. Yet another reason I picked HIP to be square as my theme song this semester, square matrices. Knew that was coming. What's on the diagonal is the variance of each variable. What's on the off diagonal is something called covariance. That is how things go together in unstandardized units. So correlation is standardized covariance. We don't normally work with covariances in terms of describing results, but they do go into models. So when you get into classes like multi-level modeling, structural equation modeling, you'll deal with covariances more. But we don't deal with them in this case because 15 is in dollar years. Because income is in thousands of dollars, education is in years, so the association between these two things is $15 years. And if you're like, what the hell is a dollar year? That is correct. All I can tell from this is that it's positive. So that means as x goes up, what happens to y? Y goes up. Yeah. So direction is all I got from this because these are completely scale dependent. They're in units. So that's why we usually look at correlation matrices instead, because then you don't have to know what the units are to make sense of the numbers. But variances are on the diagonal. So now I have my 190 that I wanted to have. Okay, with me so far? All right, let's do some modeling, shall we? The simplest little model, the wrongest model, I should say. It's empty. What does that mean? And feel free to read from the slide. No predictors. So this is something that I'm doing primarily for pedagogical reasons, because this is the best naive starting point, like in terms of beta 0. That's what we say every single person is going to have a predicted income to be, beta 0. Y'all get the same prediction. There's nowhere to go but better from here. If I don't know anything else about a person, what's my best guess for their outcome variable? The average, the expected value. So that's what beta 0 is going to be. So fitting this model then, and I have words on here, by the way, describing what else the output is about. So most of what I say is written down on here at some point. For the rest of the semester, we are using one thing in Stata to do analyses, regress. Can you guess what that stands for? Regression. Yeah. First question, it's like, what variable would you like to predict? I would like to predict income, please. What would you like to predict it from? Nothing. That's what the blank space means. Anything else you'd like to know? Like, would you like fries with that? Would you like to supersize that? Would you like to add on, our new McFlurry dessert or whatever? I'd like to add on confidence intervals, please. So what does level 95 mean? 95% confident. Said differently, alpha of 0.05. Yeah, they're inverse. So confidence and alpha are the opposite of each other. If I want a 95% confidence interval, that's saying alpha of 0.05. 95% is where expected is, and 5% is where unexpected is. 2%, 2.5% on either side. First piece of output is a table that you are going to ignore during this unit, and it will show up later. Okay? Can I just do that?
Sure.
Ignore this, except for this one number right here. 190. Does that number look familiar? That was our variance. Is that a coincidence? No, it is a consequence of this model. This model has no prediction in it. Therefore, E is how far off each outcome value is from the mean. So the variance of the E's is just the variance of income at this point. It's a semantic distinction. The variance of income is the same thing as the residual variance from this model because E is deviated from the mean only, just like in the formula for variance. So 190. The reason I'm making a point of this, in your next set of homeworks, this will be the first question that you get. What is the residual variance of your model? That's question number 1 for every model. Because if you get this right, you have the right model. You have the right predictors, you have the right outcome in the right order. Again, rest of the table, to be determined. Root mean square error is 13.7. We saw that number before too. That's the square root of 190. Said differently, this is how wrong the model is on average for each person. It's off from what is supposed to happen by 13.8 on average. That's my standard deviation of income at this point. That's my residual standard deviation at this point because we're predicting income with no additional information. Everybody gets the mean. Things you are going to pay attention to. This second little table, this is where your fixed effects are going to be. And note the similarity to the Excel table that we built earlier. Also not a coincidence. Underscore consts. That stands for constant. That is what Stata calls the fixed intercept. I don't like the term the constant because all fixed effects are constants. That's not sufficiently descriptive, but underscore const is your fixed intercept. And as I noted out here, it is beta 0. By the way, in these handouts, anytime you see words out here, that's me. That's not Stata. That's me annotating this for you. If Stata actually printed what everything meant, I would be out of a job. So I'm kind of happy that the output is difficult to read because that is job security. It is. You learn this stuff, someone will pay you because they don't want to learn it. There are many jobs that are like that. Coding and math and stat is definitely one of them. How many people, when someone asked you this summer what classes you were taking and you said, I have to take stats, had someone react like this, oh man, I hated that class. I had to take that in nursing school. Or I had to take that in business school. Or I had to take that. Did anyone actually say, oh, that was my favorite class ever? You're so lucky. Like one person. Yeah. Yeah. No, and it's funny because it's usually like when I'm at the doctor's or something getting my blood drawn and they're trying to make conversations, because I'm a wimp when it comes to needles and I'm like this anyway. Oh, what do you do? Oh, I teach college. Oh, what do you teach? I tell them I teach applied statistics to terrified graduate students. And then I get, oh, I hated that class. And I'm like, well, I hate needles, so we're even. Like you picked your job so that I don't have to do it and vice versa. So yes, I try to make things easier because that is my job. Yes, Zoomers say that is a common response. There are many jobs, right? So one of the things my doctors want me to do now is get a colonoscopy. And I'm like, oh, no, thank you. There's an alternative in which you send a sample of material to a laboratory and they analyze it and see whether you need further testing. And whenever I think like my job is bad or I feel down on whatever, I think, you know what, there's someone's job. It is to open those boxes and process them. So yeah, you think this is bad, there are alternatives that are worse. Job security, sitting in my nice organized office, typing code, watching numbers come up. It's not a bad gig. So 17, this column header is called coefficient. That is synonymous with estimate. That means this is the answer. This is the slope that gives you the smallest ease possible for your sample. It figured out what it is and it spits it out for you. This is also the way that I will use to check if your fixed intercept is correct to check your centering. So we'll see that happen in just a minute. Standard error. What does that tell me about my mean of 17? The standard error is 0.51. I'll take gestures, I'll take words.
On average, off by 0.51 with a different sample.
Yeah, so here's the thing. This standard error up here, this MSE, this is about your people. Your people, 13.8 is the average distance from a person to the sample mean. Or the sample predicted mean is where we're heading, because we're going to customize it based on predictors. Predicted mean, your people off by 13.8. This standard error says your sample is off by 0.5. This is the expected inconsistency of this mean across repeated samples of the same kind. This is an index of wiggliness of your sample mean across repeated samples. This is also known in Introstat as the standard error of the mean. Not a coincidence, because this is right now the mean for my outcome variable. T is 34. 17 divided by 0.51 is 34. P greater than absolute value T. What is that in English? That's our p-value. Now, it's 0 to 3 decimal places. P is never 0. Don't report P as 0. That is not cool. It's always going to be less than 0.000 something. Now, here's a question. Do we care about this p-value or not?
Sorry.
So if we think about p-value, the definition is how often you would expect a result this extreme if the null hypothesis were true. Yeah, we don't have any predictors. So the null hypothesis is still 0, but it's for the intercept. So this is saying if in reality the mean of income is 0, meaning the whole sample makes no money, how unexpected is a mean of 17? Well, it turns out it's 34 standard errors away from expected, because 17 is decidedly not 0. So only if 0 as a mean for your variable is something that would be of interest would this p-value tell you anything useful. And this confidence interval tells you across repeated samples what the interval is that would contain the mean 95% of the time. So this gives you some kind of imprecision estimate. I don't like these, but I put them out here because reviewers sometimes want them. And if reviewer 3 is like, I want a 90% confidence interval instead, then what?
Change your alpha.
Yeah, what do I change?
Oh.
That.
Nice.
Put a 0 there. Then you get a different one. So which of these numbers is necessary and which isn't? Only the first two. Those are the ones you only need. Because 17, the coefficient divided by standard error, is the t. This t compared to your reference t distribution, which is based on your sample size, gives you this p-value. And this confidence interval is used building in the goalpost where critical is, multiplied by your standard error. So really, these are the two numbers that you need to report at a minimum, and the rest are a conclusion of that. Level 290, say the Zoomers. Very correct. Say that again? Mm-hmm. Yeah, so this t says where you landed on the graph. Where the goalposts are a function of what alpha you chose in terms of what unexpected is and your sample size. The higher the sample size, goalposts move in, it's easier to get past them. Yep. Okay, other questions, comments? All right, want to see it in R? In R, we're only going to use one function as well, and it is in base R. It's called LM, linear models. Yep, that's what it stands for. Note that it is lowercase lm. Uppercase LM is not the same, and it will yell at you. Now this code looks a little bit different because there's some extra stuff happening. This looks like an equation in and of itself. Thing equals other stuff. The thing on the left is a name that you make up. It is the name of the object that is going to hold all of these results in little data sets in R so that you can access them and do math on them if you want to. So I am saving the results of this analysis inside R as what's known as a variable in the environment. And it's on the right-hand side by default if you have your panels organized that way. So I'm calling this model empty because that's what it is. You can name it however you want. Just keep in mind that this is case sensitive, so make sure that you're capitalizing things consistently. I usually write in title case like this. In LM, first thing I have here is what data set would you like to analyze? This was not part of the data code. That's because Stata only allows one data set to be opened at the same time, so there's no ambiguity as to which one you're operating in. In R, you can have as many as you'd like. Same with other packages as well. So data, example 2. Formula. That is, what's your model going to be? And because in R, arguments are defined after equal signs, they had to make another one. So after formula, you list the name of the outcome variable you are predicting, and then where there would be an equal sign in the equation, you put in this tilde, or squiggle, as I sometimes call it. It is a shift above the tab key on the left of your keyboard. And then I have a 1 for your fixed intercept. You don't have to have that, but I find it useful for other reasons I'll describe later. Now, if you just run this much, you won't get any output. By default, it doesn't give you anything. It saves it. And if you want to print it, then you have to ask for that separately. Now, I am asking for a print using a different package that gets me a table that looks a lot like the one I said to ignore in Stata. We're still going to ignore it for now, but I've got the 190 right here. That's my residual variance. That is all the variability in income that we don't know why yet. Under coefficients, these are my fixed effects. Intercept in parentheses, and then this column is called estimate. That is the same thing as coefficient. Here's my 17.303, standard error of 0.51. 17 divided by 0.51 is my t of 34, and this is scientific notation. So that means there's like 16 digits of zeros before we get to a number. Can I get a judge's ruling on that? Close enough? 16 zeros and then a number starts? That's because it's a minus sign here. If you see a plus sign, then it's like zeros, like millions and billions and gazillions instead. So this is a setting you can control when it switches to scientific notation versus printing all the zeros. I think I have it set to print 9 zeros and then give up and use scientific notation after that.
Question.
Yeah.
Key value here was exactly 34. On the other one, it was a little bit different.
Mm-hmm.
So does R round to the whole, or?
I think it's just printing it that way. I don't think it's not rounding it internally.
Okay. So if we needed more digits than that, then what would we do?
You would have to potentially ask for it to be printed or dig to find an object for that. But that's something that I will try to anticipate in terms of making that not
Because
necessary.
You mentioned 0.01, and obviously this is not within 0.01.
Yeah, so if you entered 33.99 or 34, that's correct within 0.01 and the homework system would take it.
Okay.
Yeah, yeah, it's correct to that level of discrepancy. Yep. Residual standard error, is that a people thing or a sample thing? One vote for sample? Person thing?
People.
Yeah, it is for one sample. This describes how far off from the predicted outcome each person would be on average. This is how wrong the model is on average for any person in your sample. This standard error right here is a sample thing. That describes the expected inconsistency of this mean across samples. All right, so summary is what generated this part of the output. Confint. Any guesses as to what that stands for?
Confidence interval.
Yeah, confidence intervals. And just like before, oh, what would you like the confidence of? I'd like it from the results of this model, please. And at what level? 95% confident, please. And there it is. You would report this, by the way, as lower and upper, because 2.5 and 97.5 are specific to a 95% interval. I'm sorry? That's two tails. Yeah, we're only doing two tails in this class. Because if you can be wrong either way, it should be a two-tailed test. That's my like philosophy. If you can only be wrong one way possibly, then I would be okay with the one-tailed test. But yeah, this is assuming two-tailed for everything.
And then when I do the Google search, it's just one tail can verify if that really positive or really negative way. But can I do it twice?
No.
Single way?
No, you can't do two one-tailed tests because that's cheating. Yeah. Yeah, you're supposed to pick your alpha and then pick whether it's one or two and then see what happens. You're not supposed to like change your mind after you see what happens as to which is supposed to be what you want to report. Yep. So the difference would be like where 5% is. So if you have an alpha of 0.05 and you want a two-tailed test, then it's 2.5 on either side of the goalposts. If it's a one-tailed test, you're loading up one side with all 5% and you're removing the other side from possibility. So it's essentially a one-tailed test at 0.5 is the same thing as a two-tailed test at 0.10. Yes. All right, how about a predictor? Education, right? More education means more money, right? Nope. Who are the people that make the most money? Like, yeah, LeBron James, folks like that. Did he go to college? I don't believe so. No, I believe he started his career straight out of high school because, you know, when you got it like that, why not? But education theoretically should be related to having a higher paying job, so it's a reasonable hypothesis. So we're going to give education a fixed slope. So now how many parameters are we estimating in terms of creating predicted outcome? 2. Yeah. So I've got interpretation questions here. These are going to go with the output down below. So in Stata, to add a predictor, regress, income is the outcome variable. That's always first. And now I am adding in education. So these names are what the columns are called. So you have to know that to be able to type that. And that is another reason why in the examples that I will give you, I will also tell you like what things are called. So like in your syntax file, you'll have the names of all the things you need to type. Scrolly, scrolly, scrolly. There we go. And order matters. Okay? Y is first, then the X's. That's a common mistake because it looks arbitrary, but it's not. And then we're back to level 95. The table that we are ignoring for now, this number used to be 190. Now it's 162. Is that good news or bad news? That's good news. That means part of the unexplained reasons, yeah, smaller, yeah, the wrongness has shrunken. Yeah, less wrong. Part of the reason why people differed in income is attributable to their education level, and so there's less unknown reasons left over. Fewer unknown reasons? Yeah, less unknown. Let's go with that. So here's the 190 that we started with. So it does show up, which is why I say empty model is primarily pedagogical. The table we're not going to skip over has our 2 fixed effects. Notice that the intercept is at the bottom. Stata always puts it at the bottom, much to my chagrin. I don't like it there. So let's do education. The slope is 1.82. 1.82. Nope, nope, that's the European version. There we go. What does that mean? It is. Commas and periods get interchangeable. Yeah. What's that mean? Who's feeling brave? The sentence starts for every.
So increasing 1 for the X, the average of 1.82.
Yeah, for every, so unit of X. So for every year of education, income goes up. Yeah, so 1.82 in thousands. So yeah, 18,200. Yep. Yeah, and we can just stick in the thousands to make it a little bit easier. But yeah, the definition always is the same. It's the change in Y for a 1 unit change in X. You just got to put the words in there. A unit of X is a year of education. Y is income level. This is a positive number, right? So as X goes up, Y goes up? Is it expected or unexpected if the null hypothesis of 0 were true? If education had nothing to do with income, is this result expected or unexpected? Unexpected, and where are you looking to make that call? Yep, that right there. So reviewing, estimate minus 0 is the null hypothesis, divided by our standard error, gives me t. Oops, not what I wanted. That's where we are on the plot. So the goalposts are like 2-ish. We're at 11. So definitely in unexpected territory. Unexpected positive or unexpected negative? Positive. Yep, that's just with the sign. Significantly positive is what I would call this. Yep. What's this number mean? 0.16. A sample thing or a people thing? Sample. This is how wiggly my slope is. On average, if I repeated this study, my slope would be off from the right answer by 0.16. So it's not very wiggly at all. 309. One more number to interpret and we can go. Yeah. Yes. Yes, 1.82 is beta 1, as labeled out here, for the slope of how education predicts income. Yep. So intercepts can be wiggly, slopes can be wiggly. Now my intercept went to negative 7.9. So on average, my reference group makes negative $7,000. How did that happen?
It's because you haven't centered your.
Yeah. Who is expected to make negative $7,000?
Baby.
Not baby,
Or
kinda. 0 years of education. Someone who never went to school. So why that happens, I can show you in a picture. I know I have that picture. I made it on purpose. Just got to find it. There it is. This picture right here. Education in years is on the x-axis. Income in thousands is on the y-axis. This is where negative 7 comes from. Because if I follow the regression line, the slope of this line is the 1.82 all the way down to 0. That's what I get. Now, this isn't wrong, but it's weird. Because we have a parameter that is reflecting nobody. I don't like it. How do I fix it? Starts with a C. Centering. So that's where we're headed next time, is to this picture. And if I subtract, say, 12 years, I redefine what 0 means. Now my intercept is going to be right here. The expected income given education of 12 years as my new 0. To the best of your eyeballing ability, are those lines the same?
How education
one
year
shifted from the other.
Question?
how education year can be negative?
Because if I subtract 12, the negative 2 would be 10th grade, negative 4 would be 8th grade. Yep.
So the minimum should be negative 12.
Yes. Negative 8 in this sample would be, I think, the lowest because it stopped at negative 10. Yeah, I didn't plot it all the way down, but yeah. No, these slopes are the same. It's kind of hard to tell, but they are the same. And as well they should be, right? Because subtracting 12 should not change how related these variables are. So that's why I say it's not wrong to not center. It's just weird because then you end up with like negative 7 for a variable that can't be negative, and that's not helpful. No, I just didn't plot it. Yeah, I literally just cut the axes to make the picture better. But yeah, everybody is still in there. So somebody like who had 0 years of education would have negative 12. Yep. Yep. Remember, the intercept is the you are here sign of the model. You got to know where you are before you can talk about what happens as you go up or what happens as you go down. Being in the middle is helpful to think about that. Okay. Okay, 3:13. Questions before we call it a day? Zoomers, anything from you? Thank you for the comments in the chat. I appreciate that. All right, then homework 1 for real due tomorrow. If shit breaks again, please let me know, but I'm really hopeful that we fixed it. Office hours tomorrow as well if you have any other questions, okay? Bye for now. Thanks for being here, everybody.
Can you turn the page to the syntax?
Yes.
Because I have some question in